All right. Next, we want to continue our idea of counting, and let's run this again. There's another important theory here where we want to find the probability of A union B. A and B can be anything. Remember, we were saying A is the tall students, right? B will be the male students, right? So tall or male students, not tall and male, but tall or male students. So A union B. So how do we go about it? Well, you can see from the graph that just means count any ball within this outline of A and B, right? This shadow outline of A and B. Yeah. So that will be 6 here, right? So 6 out of 10. But how do we generalize it? So using the count concept, we have counting A union B because we just copy and paste it here, divide by count of U. But counting A union B, we can now easily understand the counting process. Yeah, so count of A, so we have included the yellow balls one time. Then count of B, because everything in B must be counted. And then we included the yellow balls second time, right? So we have to minus one copy of the count, the number of balls inside both A and B. So we do that. And we can see that very easily in the picture. So after you do that, then you just split them all up. CA over CU, that's P of A. CB over CU, that's P of B. And C of A intersect B over C of U. There's no easier way to simplify that. So we minus P of A intersect B. That's it. That's the common expansion that we see in most textbooks. Another way to sort of derive it is that we can also use the idea that if you look at the balls here, right, um, A union B will be these 6 balls, right? Another way to think about it is total 10 balls minus those that are outside A union B, right? Minus those that are outside A union B, and that's basically what we want. So very simply, we can express the balls that are outside as A prime, right? A prime will be this whole thing, this whole thing outside of A. And then B prime will be this whole thing outside of B, all right? And we intersect them. That means the common ones are retained. And so that leaves us the entire area outside of A union B, and that becomes A prime intersect B prime. So by counting, it's way easier to see why, yeah, than to just directly see, hey, look, isn't it clear and obvious that P of A union B is 1 minus P of A prime intersect B prime? Sorry, no, it's not obvious to me. Yeah. Okay, so draw a picture, fill in a few balls here and there, or else you can also use pictures. Sorry, the areas. All right, you can put a 3 here, you can put a 2 here, you can put a 1 here, so that you don't have to draw so many balls. And you have to imagine a little bit. The 3 means 3 balls, and so on. But idea is there because you can visualize it. It makes it easier to understand what's going on. Next, we want to talk about conditional probability. This is one area that is, to be honest, very confusing to me when I was learning this stuff because of the word conditional. It kind of wanted me to think about the a criteria, it's like a condition. Upon fulfilling, then there's a trigger of some probability or what? No, that's completely way off. There's no condition and there is no trigger, and the best way to I would ask you to think about conditional probability is that it is just a different way of calculating probability where the denominator is to be specified. Normally, we just say, what's the probability of A? We don't talk about the denominator. Why? Because it's always count of U. It's always the universal set. Conditional probability, again, I'm telling myself, ignore the word conditional. It's a special probability where the denominator is specified in the question. So temporarily, we ignore you and we talk about a subset of you there. That means it's not you. We don't throw away or redefine you. You is still there, the universal set is still there, but we might want to temporarily, right, in this line, in this chapter, in this paragraph, temporarily talk about a subset as the denominator. So you notice that the definition is count of everything that is in A and also in B. Actually, it will be count of everything that's in B that also belongs to A. So it's more like already inside B, but that part that is in A, then divided by the count of B itself. Literally talking about looking at this B as you, looking at this subset B as a temporary universal set, and count those items of A that also belong to B. Because if you count all of A itself, the ratio will be more than 1, and then we have a problem, right? So probability cannot be more than 1. So count of those A items that are also in B divided by count of B itself. So if you want to answer this question, P of A given B, that is 2 divided by 3. Yeah, okay. And well, that's sufficient. But we can also say, what is P of B divided by A? Well, that is count of those balls inside A, but also belonging to B. That's why B intersect A, divided by the count of all balls in B, in A, sorry. Right. The denominator is given by the letter after the vertical bar. So this is very important. A little bit like fraction, but not exactly. So the vertical bar, you can think of it as given that. All right. So probability of B occurring given that A has occurred is count of B intersect A divided by count of A. So let's just quickly try it out. Count of B intersect A, that's 2 balls. Divide by count of A, that's 5 balls. So it's 2 over 5, and that's correct. Okay. So far, so good. Okay, why this? Why do we want to retain the universal set and then temporarily, for some reason, divide by a different subset as if it were the new universal set? It's very simple, because if you can imagine, like I always do, that we're doing a census survey, so we are basically knocking on the doors of every household and doing a population check. Yeah, so we will ask those households a few questions, and then we do a study of the population. Then you can imagine that once we are done with the huge effort of data collection, right, we will summarize that into a report. And for instance, we might say um, the fertility rate, yeah, so the number of child in Singaporean households based on our data is, we can divide, right? So let's say number of child in our Singaporean households is 1.5. Okay. So that's about the entire Singapore. That's the universal set, because the entire census is done for this whole country. But in one of those chapters, we might want to talk about senior citizens. Yeah, okay. So we might want to say something like, uh, amongst those that are 50 and above, for example, the average number of children in those households is, however, 1.9. Does that make sense? Yeah, okay, because maybe earlier days, the now older households, they have higher number of childbirths, right? The contrast, therefore, is going to tell us, okay, interesting. That means the newer households, the younger families, may have way below 1.8, 1.9 on average number of children. And so that is averaging the entire country down, right, to 1.5. So this kind of contrast is still all about Singapore. So we don't want to discard, or we don't want to discard this universal set of studying Singapore population, because after all, this older households, they are part of the universal set, right? However, we want to express a subset because this particular chapter 8 is talking about senior households, okay, 50s and above.